Hello, this will be a demonstration of Proposition 12 from Book 10 of Euclid's Elements, which says that magnitudes which are commensurable with the same magnitude are also commensurable with one another. We'll have two magnitudes, A and B, both of which will be commensurable with a third magnitude, C. And we will want to show that these two magnitudes, A and B, are not only commensurable with C, but are also commensurable with one another. We want to show that A is commensurable with B. Now, because A is commensurable with C, we know from Proposition 10.5 that commensurable magnitudes have to one another a ratio of two numbers. So because A is commensurable with C, we will be able to set out two numbers, D and E, such that the ratio which A has to C is the same as the ratio which the number D has to the number E. Now, similarly, because B is also commensurable with C, according to the same proposition, 10.5, we will be able to set out two numbers, F and G, such that C is to B, just as the number F is to the number G. Next, we'll set out three more numbers, H, K, and L, such that H is to K, the number H is to the number K, just as the number D is to the number E, and the number K is to the number L, just as the number F is to the number G. We can create these three numbers, H, K, and L, according to Proposition 8.4, which lets us create a quasi-continuous proportion where each term has to the following one a certain ratio, not necessarily the same ratio, but just a given one. So that's how we're going to create the numbers H, K, and L. So that H is to K just as D is to E, and K is to L just as F is to G. Now, because the numbers D and E were created such that the ratio is the same as that which A has to C, and the numbers H and K were also created such that their ratio is the same as that ratio which the number D has to the number E, we have two ratios, A to C and the number H to the number K, which are both the same with the same ratio, the number D to the number E. So we can say, according to Proposition 5.11, that those two ratios are the same with one another, so that A is to C also as the number H is to the number K. Now, similarly, we can show that C is to B just as the number K is to the number L. Also, because of how we created the numbers K and L, their ratio is the same as that which the number F has to the number G, and the numbers F and G were created to have the same ratio as C and B. So C has to B the same ratio which the number K has to the number L, but we had also shown in the previous step that A has to C the same ratio which the number H has to the number K, so that we can therefore say X.12 across the middle terms of C and the number K, we can also say that A is to B, just as the number H is to the number L. That's Proposition 5.11 that lets us do that X.12 crossing the middle term move. So A is to B, just as the number H is to the number L. But we know from Proposition 10.6 that magnitudes whose ratio is the same as the ratio of two numbers are commensurable. Because the magnitudes A and B have been shown to have the ratio of the number H to the number L, their ratio is the same as a ratio of two numbers, we can therefore say, again according to Proposition 10.6, that they are commensurable, so that A is commensurable with B, which is what we set out to demonstrate, so we are done with the proposition, therefore, etc., Q, E, D. Similarly to the previous proposition, we're again proving that commensurability, not incommensurability, commensurability specifically, has another property that we like about equality. Namely, the technical word is transitivity. We know from Common Notion 1, this was set up from the very beginning of the elements, that if two magnitudes, or two things, broadly speaking, if two things are equal to the same thing, they're also equal to each other. And we've just demonstrated that the same holds for commensurability among magnitudes, that if there are two magnitudes that are commensurable with the same magnitude, they're also commensurable with one another. And Following propositions will show that commensurability and incommensurability have more of those nice properties we like about equality and inequality. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 1013.